Welcome, everyone. Thanks for being a part of today's presentation on the digital thread for defense. My name is Sean Waddle. I'm with MTech. Now, our company works with engineering designers and analysts in the commercial and DoD sector really become more efficient. We may be helping them modify a single part for a structural modification on an aerospace platform or optimize their designs in less time while seeing it all the way through testing, fabrication, and certification. Now, we do this with cost utilization and market-leading resources on one of which being Siemens Digital Industries. I'm a certified professional with Siemens and am able to offer some of these solutions. Today, we're going to talk about changes in the overall defense industry and changes that will eventually be the new methodology, for designing aircraft and other defense projects. Obviously, something that a company like MTech would very much want to concern ourselves with. The initiative was created and spearheaded by the former Assistant Secretary of the Air Force for acquisition. This was Dr. Will Roper. He wrote a paper a while back, actually, called There Is No Spoon, and it really just put forth the ideas here that will change the way that we design and build airplanes. And the idea is to go much faster than we are now. We're simply taking too long to design a plane or systems or parts to really get them out. Not because of incompetence, quite oppositely, we've become so good at engineering the components, but the challenge now resides in the complex integrations of those components. The systems integration now takes anywhere from 30 to 80% of the total project time. We combat this with what Dr. Roper drew up as the digital holy trinity, which are three elements of design that he believes will revolutionize the way we go forward with design and aerospace and defense. The first is digital engineering, which is model-based systems engineering, and we'll see a lot of that in this presentation about using simulation to understand what we're building in detail before we build it. Not only how we'll be building it, but how quickly we can build it. The digital engineering gives us access to agile development, which allows teams to iterate quickly on a working design and improve it through each loop, through the iteration, and all of that is being held with open architecture based on cloud-based computing and open access across organizations to the same set of development tools. Now, MTech and Siemens have been working with the Air Force and with the Navy to bring this to fruition and pull this together to create a digital backbone that would be used across projects. And here are some of the projects that it's worked on. The TX Trainer, the Ground-Based Strategic Defense System, submarines, tankers, bombers, all of these types of developments are coming together with the Air Force and the Navy working with Siemens using Accelerator. MTech, of course, is known for performance engineering and deep-level analysis in the world of aerostructures. Siemens is chosen for this work because it is a trusted name across all of their space and defense, providing services across the whole range of mechanical CAD through ECAD simulation, and then importantly, here we'll see PLM. In fact, the Air Force has mandated that projects working with the Air Force are going to use Teamcenter as the PLM center for the project, and we'll see why in the next slides. So unless they, I suppose, get a waiver, they'll be working with Teamcenter, and so will we. So the concept of the digital twin and the digital thread are related. A digital twin is something most of us are comfortable with. It's a model of a real device. In the aerospace world, we use various simulation tools and more physical simulation tools, and we create this virtual product. which is what the plane characteristics is going to be and how it's going to be shaped. And we can use that to start to show how would we build such a thing and create a virtual production line. This is how the parts will fit together and where they'll fit together. And then we'll iterate back and forth between those two, making this really through the agile process, making the plane better and better, until I guess it's ready to go to real production. And at that point, we automate the factory and make a digital twin of the factory, make sure that the assembly lines are balanced and that the system can move forward in that way. We ship the plane. We have a digital twin of the real plane, and we're using that to track defects and to track customer support issues and service issues and feed those things that we learned back all the way to the beginning of the process, so as to improve later iterations of the same aircraft. Until now, we've had this sort of picture where you have the Department of Defense that's going to define what it needs to be built, and then the industry that supports it. And there's this gap between the two. Defense is up here, and the industry is down here. These are the milestones that we've had for decades that go through all of these steps to build a plane, and two of the ones that we're going to look at, program award and program delivery. Those are the two that people know the most in the process. Take the current B-21 rollout right now. We think about this process. It's two organizations taking all of their intellectual property that they have in their organizations and essentially dumbing it down to paper. We are giving paper back and forth today, and I suppose that's they're in PDFs, but still it's paper. And so this is the state of affairs up until recently. Almost a decade ago, the Department of Defense started to say, well, we need to start to use PLM systems for this, and they said that data would have to be delivered in XML, which works much better with Teamcenter. Now, if we look at what's happening, it starts out in the Department of Defense with them defining the project, and then once the program's awarded, it goes into the industry. So the Department of Defense is doing the requirements and the systems engineering and then analysis of alternatives. Meanwhile, passing paper back and forth from the industry to iterate on the process. We have cadence meetings. The industry now has the requirements, management, design, simulation, and this is following multiple tracks as the program is built and delivered, and more cadence meetings, and again, paper, and eventually an airplane. Meanwhile, one side is actively working on the project and the other side is doing shadow work. When the project is being defined, the industry is trying to help guide it to where they can build it. While it's being designed and built, the government is watching and providing oversight of the project. And again, paper, going back and forth, cadence meetings. That's what we want to get rid of with Teamcenter and Accelerator. It looks like this. We create one unified system across two organizations where we're no longer passing paper back and forth. What we're passing back and forth is models in the original design data. And that allows us to take this process and shrink it. The program award happens faster and the program delivery happens faster. We've had plans now with this system to be delivered and built in 18 months, and it's an agile system. So this plan delivered in 18 months is the first iteration of the plane. It flies. But then you can start to add ordnance to it. You can start to add other systems onto it. But you now have something to work with and the models to build upon. When we think about how this process works, there's still a lot of steps, but the steps are now part of an organized flow between two organizations, and they don't have to send paper back and forth. They're all looking at the same database, and they're all looking at the same data. And you don't have to do this with one partner. If you're going through this process with one partner or a vendor, you could be going through this process with another partner. If you were the DoD and you find out who is going to deliver you the best plane, or a third, or you can say maybe take another partner and use them for fielding the plane. So, you have flexibility, multiple projects, multiple partners across multiple phases, all because everybody is using a centralized database system to hold design data. So let's look at a demo, so to speak, of this process. So we're going to say, let's say there's a project and we need this project, and we would know how that would work. Well, think about all of this project would be this is the project is the fact that we have soldiers who are in the areas with IEDs, and we want to have something that flies, an airplane or a helicopter, and looks for IEDs, and as it flies along, it has sensors that recognize IEDs. They can send back locations and requests to take them out, and then it can take the ideas out before the trucks roll by. Either in this case with the super cool laser, or maybe with simply a missile. But this is the basic idea of what the DoD wants, a very simplified idea of what the DoD wants. So how does this start? How does this happen? So let's look at this processing. We're going to look at each step and a little demo of how each of these steps would work. Right at the beginning, we're doing requirements engineering, and this is critical. Mistakes that are made at this early stage that don't get caught are hugely expensive. They completely change the architecture of the following designs. They may create bottlenecks in materials or bottlenecks in manufacturing. Things way back at the beginning here that are not fully understood can wreak havoc with the rest of the project. And so here we're taking those requirements and decomposing them, so as to get some sense of how these requirements will get turned into a design before we move on to the next step. There are going to be multiple ways that we can solve a problem, so we can use these alternatives like the aerial platform. We don't know if it's a plane or a helicopter, but we know what it should be able to do, and we could put what it should be able to do in the functional models that show us whether the system that we're thinking of can either work. And if it can't work, we can now iterate online early on before we start to get the industry involved in defining, what's physically able to be done. So at least now we have this model of what we want. And now the industry can get involved in beginning to shape it before there's even an award made. The industry can be showing different ways, different physical ways that the design could be put together. And one of the capabilities of the real world to implement what up until this point was a theoretical model. And so the industry now passes these back up to the DoD again through a system that they are working in together, and the DoD can now look at what the alternatives are for that. And so when you get to the analysis of alternatives in the award program, right, you can now look at different bidders and how close they are to what you need, and whether or not their design is too expensive or too hard to build or too hard to maintain. All of this can be simulated up front, and you can look at better one or better two, and here's a helicopter design. That turns out it doesn't make it, and then a different kind of airplane, try it that way, and that didn't really make it. And so you finally come down to this guy, and here is the winning bid. And now the project has passed out of the DoD and into the industry partner who won the award and who is starting to build a design using a model and simulation technologies, looking at different ways and different approaches that could be used to implement what this partner helped create as the specifications. The design gets decomposed into smaller and smaller parts. The parts have their own parameters about how they operate, and you can find out about failure rates and failure modes and things that don't really work very early on in the process. We go and start to design different pieces of it together. We need electrical, we need the airfoil, we need metal, we need to hear the electronics, right? How hard are they going to get and how do they fit together? So all of this is simulated as you go, and all of these pieces of the plane are in the database so that everybody in the project sees all the parts of the plane fitting together. And so you can see here how you could try different shapes and simulate the stresses on them and come to some early decisions about your design. While this is all going on, the government in its oversight capacity on the secondary path can also look at the design as it's running and come to make sure that the plane is doing what it's supposed to be doing. And so rather than going into a physical plane and opening up and looking at all the pieces and looking at how it fits together, you take this model of a plane and open it up and see how it's put together, what they cost, do they meet the requirements of the project. You get into, much broader sets of parameters that you can look at, see how it's structured. The plane is essentially built in a virtual space, and when you can, in that virtual space, take the plane, take some of the parts off, look inside, see what's what. So this is all being done by the government in the process of doing it. You can even look at the manufacturing techniques that might possibly be used to simulate, maybe we'd take a drill here, and how would a drill be used to put this part together, this actuator. Now that the design is inspected and approved, we can get into more detailed simulation. Now, in this case, we have a look at the landing gear system, and we see how the wheel comes up and how it pulls in. So we can look all through the plane and simulate different elements of it. This is, I think, of where IC design comes in. We are able to look at the heat we're generating, the heat, the batteries, airflow, how it's all going to fit together. Now that you have the plane designed and are ready to go, you got to think about how to manufacture it. You have the manufacturing flow where you see how the pieces will fit and also how you create the instructions for how to make it. So that while as you're simulating, you're also creating instructions following the cabling, making sure that it all fits, and then seeing the process, the steps, how and what order we will add the parts to this box to get the box ready to be installed in the plane. And we have virtual reality, ways of looking at the actual size of the plane it's being built into, and all the pieces, how are they fitting together? Can all the tools reach it? And you may be looking at a design that you thought was going to work, then you're going, oh, well, that this part of this plane gets tripped over against this part of the plane, and that's not going to work. And so we can get all of that done even before we actually build it. Now we know how to manufacture the plane. We can go and simulate these the shop floor where all of the planes are going to be, how the parts are going to fit together, but more, how much space does it take, and what will be needed to do this manufacturing. All of this can be simulated in Team Center, and all of these specifications about the factory and the actual places that could be used to build the factory are uploaded into Team Center, so that everybody has a common look at the way these parts are going to be put together. Now we've shipped the program delivery, and we want to see, now it's out there. How will it be built? The digital depot will let us look at where the parts are built, where they're going to be shipped, how far are they going to be shipped home, with the path that the parts are going to follow. Is there anything that would get in the way between one plant and another? All of this is simulated, so the scope scope of the simulation is spreading out over the course of the project so that we can have a more efficient manufacturing system without any surprises, such as a tunnel or something that blocks a critical piece from being trucked from one place to another. And then finally, you have a plane that's out there. It's built. Now that the plane is shipped and built and out there, it's going to need service. We're going to find out that there are parts of the plane that are not going to be working the way that we thought that they would. They are wearing out more quickly, or their elements in the way we were describing, say they aren't working in the field. And no matter all the simulation we do, it's eventually going to be on the field, and someone's going to work at it. And that data is also captured and is put back into the system so it can be wrapped around the closed loop and improve the next iteration of the plane, or improve the parts that we're putting in the planes. So you can see, for example, this piece, this wheel actuator, that we're going to see how someone would work with it, so that if a service tech needs to replace the thing, there and there you see where it is. You make sure that it works, and you keep track of the stats about how all the different parts are going, are doing, and what it's costing to maintain this plane. So now we've worked through the whole seamless flow. We've had one viewer plane shared by the Department of Defense and industry. Both sides are constantly working with the same model, and the model goes through the thread from design requirements over here, constantly being improved and worked upon until it ships over here. And this process from here to here, could be as little as 18 months, and has been as little as 18 months for a brand new flying platform. So how does this affect us? Well, we've reached a point that we've gotten so good at the engineering of components, and that we're also pigeonholing our ability to complete our full system validation of the requirements on time. We mentioned the industry is spending between 30 and 80% of their time on systems integration. Multiply that time by a number of subsystems, components, and vendors, put it in a linear reporting structure, and you can see why there's months to years of delays on the line. Imagine now shifting this all left. Imagine receiving a model, and as contractors or even subs, we're going to invest our IP, while at the same time other contractors in their fields and in their disciplines are also working to pass their models back into Team Center so that they can be a part of this higher level simulation, all drawing from a single source of truth, updated as part of one central model-based ecosystem. And in the end, what happens is we take this plane or assembly or sub-assembly of a plane that we conceived of electronically, and we find that we've got an actual plane, that the project we worked on had low risk and much faster turnaround, because all the parts of the team, the team of teams really, were able to work together simultaneously. Now, I hope we were able to provide just a small sample, a life cycle process today of a defense digital thread in model-based engineering. This is by no means a simple adoption of tools for system ready, but the purpose is to get us all thinking in this manner of integration and model sharing. Time and specifications no longer allows us to design and interrogate, build, test, and certify by pushing paper from desk to desk. Now, our team is here to help you adopt any and all of this approach. And I just want to thank you for joining us today.